Okay, so we're ready to get back into our handout, and we have just one last page and one last problem that we're going to be looking at. This is not a homework problem. It used to be a homework problem. I took it off the homework because we're doing it together here in class, but it is going to be problem 624 from our book, page 163. I'm sorry, 627. So we're doing it here in class, and it is this water bath. So it says here the device down here is a sloshing or a water bath used to wash vegetable produce. So this is going to be kind of the bucket that the produce is going to go into. And then down here, there is a crank. And it says, for the configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath. So the water bath is right here. And so that means that that's going to be the angular velocity is, how fast it's going, oscillating back and forth here. So it's going to be like a W. Angular velocity, which is going to be lowercase omega, is going to be the symbol. As the crank, which is right down here, the crank is driven counterclockwise at 100 RPM. So that is going in this direction, and that would be what we would call our angular velocity, W2, for our crank here. So first things first, as we go, you're going to notice that we are going to draw the kinematic diagram in CAD to scale. So the numbers that we see here are going to be in millimeters. Okay, so you're going to want to bring up your kinematic start file that is for a metric drawing or a metric kinematic diagram. And we're going to draw the kinematic diagram in the position that it is. So all the information that you need, scooch back in, is going to be from this diagram. So what I'm going to do is I am going to pause the video. I'm going to draw our kinematic diagram in AutoCAD, and then I'll be back. Okay, and we can continue from there. Okay, so now we're ready to kind of take it to the next step. I drew my diagram. I kind of double checked all of my dimensions, make sure my geometry was good to the dimensions that were in the book. Now we're going to go back underneath, and we are going to follow along with our procedure here. Now, the next thing that we're going to do is we are going to use the relative velocity vector equation to solve for the values that we need. So as we look here, we need to find out what the W4 is of link number 4. So if link number 2 is our crank, link number 3 is our connector, and then this is the bath, right? Number 4. We want to know, what is the angular velocity at this moment in time when our crank is going at 100 RPMs counterclockwise, okay? So this angular velocity is determined or relative to the angular velocity of link number 2, and then they're not directly connected. They're connected through this relative link. So the equation that we use, the vector equation that we use, is for straight line velocities. So we know that it's going to be the velocity of the unknown. So I'm going to put UK is going to be equal to the velocity of the known, which is K, plus vectorially the velocity of the unknown relative to the known. Now, right now, when we look here, the place we know the most information about is here at link number 2, right? We know how fast link number 2 is going. We know how long it is, okay? And then we have the endpoints identified, okay? Now, if we look here at the endpoint of link number 2 is point B. And as we've seen by just looking at that link, we can get what the velocity of that endpoint would be, okay? We know how fast it's going. We know how long it is based on the diagram in the book. So our known velocity, straight line velocity, is going to be the velocity out here at point B, okay, at the endpoint. So I'm going to draw it here, and I'm going to draw it I'm going to try to make it off just a little bit so that it's not in line with the link. But my velocity of B is going to be perpendicular to link number 2, and it's going to go up and to the left in a direction of rotation. Okay. So my known link is going to be the velocity of B. Okay. And I can calculate its magnitude because I know how fast that link is going and how long it is. So I'll be able to get its magnitude and direction. Both will be known after step number 2. Plus vectorially. Okay. We're going to leave that open. The unknown velocity is going to be at the end of link number 4, which is going to be the velocity of C. Okay. So the velocity of C is going to be our unknown. It's dependent or relative to what's going on at B. Now, as we look here, I anticipate this is going to be rotating in a counterclockwise direction as well. So the velocity of C should go up and to the left, but we'll confirm that direction. But we do know it's perpendicular to our radius of rotation, but we don't know its magnitude. We know direction, but we don't know its magnitude. So we're going to put a little circle here for magnitude, but we do know direction. And then we're going to go back over here. The velocity of C relative to B, or the unknown relative to the known, is going to be on that link connecting the two. So C relative to B. And here we are going to have a vector. We don't know if it's going up and to the right or down and to the left, but this is going to represent the velocity of C relative to B, perpendicular to the line connecting C and B. And here we can say we don't know magnitude, but we do know direction to be perpendicular to that link. So again, as we look at this relative velocity equation, once we calculate the magnitude down here of velocity B, because we will be able to do that, we then have our two unknowns separated by our equal sign, okay? And once we get the velocity of C, we'll then be able to calculate W4, okay? So let's find the velocity of B. We know that through that equation, velocity of B is going to be equal to the angular velocity of the link that it's on. It is on the endpoint of link number 2. So this is going to be W2 times the radius back to its center of rotation. So we're going to call that radius 2. Okay. So now we're going to put our values in here. We know that the angular velocity of link number 2 is 100 RPMs. Now, we know that we can't put the RPMs in here, so we need to convert 100 revolutions per minute to radians per second. Now, make sure you cancel out, okay? Don't just write this out and leave everything uncanceled. That happens a lot, okay? I want to make sure that everything is top bottom and that the units that are left over that are not canceled are what we're looking for, which in this case is radians per second. So what do we get for our W2 in the appropriate units, radians per second? $10.47. Yep, I got that too, Aiden. Thank you. And then just confirm. So it looks like it's going to be a good number. Now we're going to use this value over here. So this is going to be 10.47 radians per second. Make sure you put your units in, times the distance that B is from its center of rotation. And from the illustration, it was 80 millimeters. So you should get a magnitude of 837.6 millimeters per second. Did you guys get that? Same number? Yeah. Okay, perfect. Good, good, good. Thank you. So now that's the magnitude of velocity of B, and we know its direction. And again, our only two unknowns here are going to be the magnitudes of C relative to B and C. So now we're ready to kind of take this to our vector equation. So down here for C, calculate. I'm going to cross that out. I'm going to say graphically determine VC using the relative velocity vector equation. Okay, and that's going to be our VC is equal to VB plus vectorially C relative to B, where we know magnitude and direction for B, but then direction only for C and C relative to B. And this we're going to perform in AutoCAD. Okay, that we're going to perform in AutoCAD. All right. Yeah, so we're not calculating it. We're graphically determining the velocity of C using that relative velocity vector equation right here. So now let's go over to AutoCAD. Okay, let's go over to AutoCAD. Now that we have our diagram in place, okay, we're going to use this. And this is why it's really important that it's the correct size and orientation, because now we're going to use it to get the directions for each one of our vectors. Okay, so we need to start where we know the most information. We know the most information about the velocity of B. We know its magnitude is 837.6 millimeters per second, and we know its direction is going to be perpendicular to link number 2. So I'm going to go to our diagram. I think that's just a test. I think we're okay. And what we're going to do is we are going to draw a line, and I'm going to go randomly kind of out here. And I just need it to be perpendicular to link number 2. Make sure it's perpendicular here. There we go. All right. So my line, even though if it doesn't have to intersect, it just has to be perpendicular to link number 2. Okay. Oopsie. Okay, so now this is just the direction. Okay, this is just the direction of the vector. So what I'm going to do is I am going to actually select it. I don't want it on the object line layer. I'm going to put it on object 2 just so it's a different color. Okay, that's all. And now what I want to do is I want to make it the appropriate length. So if I go back underneath here, if you recall, the length of link number 3 was 800 millimeters, and our velocity B is 800. So we can keep it the same scale. Does that make sense? Okay, because it's going to be about the same size anyway. So I'm going to go back to AutoCAD. I don't have to worry about scaling anything. And I am going to draw a circle center radius, and I'm going to start my center at one of the endpoints. And I am simply going to have the radius as 837.6, which is the length of link B. And now what I'm going to do is I'm going to trim away the portions of the line that I don't need. Okay. That way, as long as this is right now from the center out to the radius, that is 837.6. So then I can get rid of my circle. And I am going to add my arrowheads going up and to the left for the direction of my vector. And I'm going to move this to be at the center of B. Okay. And then I'm going to label this the velocity of B. Okay. So that's my first vector. Vector VB, we know both magnitude and direction. Click save. So we've got velocity of B done. Then we need to put in place the velocity of C relative to B. C relative to B is going to be perpendicular to link number 3. So go back to AutoCAD. I am going to go to my object 3. And I'm just going to draw a line random out here, perpendicular to that link. There we go. And we're just going to label it velocity of C relative to B. No arrowhead on this one because we don't know which way it's going. We just know its direction, being perpendicular to link number 3. Then the last one we're going to do is going to be the velocity of C, and it is going to be perpendicular to link number 4. So I'm going to do a line. It's going to start randomly out, and it's going to go perpendicular to line perpendicular to link number 4. And then I'm going to move it because it will be at point C. I'm pretty sure it's going to go up and to the left, but I'm not going to put an arrowhead on it because I'll get its actual endpoint when I do my vector diagram. And this is velocity of C. Okay. All right. Okay. This is one of the screenshots that you will take. I want to see your vectors in place on the diagram so I can see that you use the diagram for the orientations. Okay. All right. So now that I have kind of like in place all of these items, now what I want to do is I want to perform the actual vector equation. So starting with the velocity of B, I am going to draw a crosshairs, right, or an origin. And I'm going to do that over here. Make sure that it's large enough so that we can see it. Okay. And I'm going to remember to copy your vectors and their labels from the diagram. Leave a copy on your kinematic diagram. Okay. So this is my velocity of B. Then I'm going to add to it on its tip. We're going to place the velocity of C relative to B. So I'm going to go kind of along its length because I don't know if it's going to go up and to the left or down and to the right. And again, leaving a copy back. So now what we've done is for this equation, I've done the velocity of B, and on its endpoint, I put C relative to B. We're going to cross over the equal sign. So we're going to start back at the origin with the tail of the velocity of C. So I'm going to copy velocity of C, and I'm going to go nearest, and I'm going to go down here. There we go. And what I want to find is I want to look where my intersection would happen between the velocity of C relative to B and C. And it looks like it's going to be like up here. Okay. So I need to just make a line. I'm going to make kind of a generic line like this so that I can extend these lines so that they cross. Okay. And I just needed a line out here. Otherwise, AutoCAD isn't going to extend anything. So now that I have this intersection, I can kind of move things around here and I can trim off the parts that I don't need. Okay. So you should end up with something that looks like this. I don't have arrowheads yet, but we'll determine that in just a little bit. So velocity of B at its endpoint is C relative to B, and then velocity of C is starting back at the origin out to where it intersects C relative to B. So back underneath here, I've got everything here. Now what I want to do is I am going to place my arrowhead for C relative to B. Since this is a vector addition, that means the tail of C relative to B is going to be at the tip of B, which means that its tip then is going to be up and to the right. So I'm going to go here. And that will be my arrowhead for that one. So up and to the right for C relative to B. Then, if I look back over here, I cross the origin. The tail of C is going to start at the origin, and its tip is going to go to the last arrowhead on the right-hand side. So, change this to object 4. The tail is going to start at the origin. Its tip is going to go at the tip of C relative to B. So I'm going to do another line here, like this. Okay. Now, before I go too far, I don't want to forget, I do need to put my vector equation in place here. So I'm going to put that right down here. I'm going to extend this out, and it's going to be VC is equal to VB plus vectorially VC relative to B. Okay. Just make sure you show that diagram that way for official. Okay. Now, the vector I'm most interested in is the velocity of C. And the reason it's velocity of C is because ultimately I need to find out what W4 is, okay? The velocity of C is on the endpoint of the link 4, okay? So once I know what the velocity of C is, it'll help me to then calculate W4, okay? So velocity velocity C is the one I need to know. So I'm going to change this to my notes layer, and I am going to put an aligned dimension on here, endpoint to endpoint, and you should get 815.02-ish. Does that sound good? 815? Jacob is nodding. Rainer is nodding. Okay. 813, then I don't know. I'd want it to be a little closer than that. 814. 814.9. That's close. That's close. 815. Okay. So what I would encourage you to do, if you're not getting something super close to 815, go back and there's something in here that isn't the right length or the right angle. Okay. So I don't mean to chase that so much, but 813 seems a little more than I'd expect. Okay, Aiden. If you were 814.9, I'd say, okay. 814.8, okay, but 813 seems a little. Also, always double check that. Number one, when you are getting your dimension here, 18, I know, I don't know if that's close enough. That seems far out. A couple things to check, Aiden. Number one, make sure you're getting endpoint to endpoint. okay, when you get your dimension and it's an aligned dimension. The other thing you want to check back here too is when you do these, make sure that your lines are going to the endpoints and they're not at a weird spot here and that everything is catching where it's supposed to be, okay? So, and the reason I'm being a little picky on that is because when we have CAD as our tool, we should get pretty darn exact numbers, okay? As long as our geometry is good, and that's going to be a result of that. Okay. So now that we know this dimension, we're going to go back here, okay? And we're going to calculate our W4, okay? So W4 is going to be equal to, so this is the angular velocity of link number 4. And that's going to be equal to the velocity of C divided by the radius of, or the length of link number 4, okay? Or the radius to C, however you want to put that, okay? So if we put this out here, our dimension from AutoCAD is 815. I'm going to just do 815. That's it. And Aiden, use that number for your example. Just be, I don't want you to chase it. And if anybody else is close like that, use the 815 in the calculation here, but know that when you do your homework, you're going to want to double check and triple check those, the construction and the geometry. So we're going to use 815 here, okay? If we go back underneath, our units are millimeters per second. So our units for VB were millimeters per second. This is going to be millimeters per second, okay? Divided by radius 4. So the length of link number 4, 720 millimeters. Okay. Now, before we do the math here, units. Millimeters is going to cancel out millimeters on the bottom. And we're going to be left with nothing per second. Or are we? What magically appears? Radians, exactly. So when we take our value of 815 divided by 720, we're going to get 1.132 radians per second. Okay. Now, this is the number that you're not going to leave as a final answer. What are we going to do next? Convert it to RPMs. Exactly, revolutions per minute. So you're going to continue on here. We're going to say 2 pi radians in 1 revolution, right? Radians cancel. And then we know that there are 60 seconds on top in 1 minute. Seconds cancel. So our W4, we're going to report in RPM. So 1.13, 60 times. Should be 10.79, 10.8 RPMs. This is a box around final answer. It's not fully defined yet. We still need direction. So this is the magnitude of W4. What's its direction? So if we confirmed that velocity of C is going up and to the left, right? We go back underneath here. That's what we kind of assumed up here, right? So if it's going up and to the left, and I put my finger at D and I pull in that direction, what is the direction of W4? Clockwise or counterclockwise? Yes, so make sure and back here you put counterclockwise, okay? Because we need direction of rotation there as well. Okay? Right. Now, handing in. This is the last page of our handout, okay? So make sure you have all the information here, okay? And if we go back to AutoCAD here, the 2 screenshots you need is the one on the left-hand side here showing me not only your diagram, but your velocity vectors and or directions, velocity vector directions in place here labeled. Over on the right-hand side, you need another screenshot for the vector diagram with VC dimensioned, okay? And then that'll complete our practice problems. Now, I'm going to let you in, so just pay attention here if you're not right now. You're going to notice that we have a couple more slides here. Example 6.6, we are not going to do. And then it says here, you can now hand in your practice problems, and it says, and example 6.6. We're not doing example 6.6 for practice problems, okay? That's as far as we're going with the practice problems. So you're just going to hand in example 6.1, which was the very first example we did the first time we met, and then everything that we have in this handout, including the screenshots for the last two examples we did, okay? So if we go back to our practice problems, that is consistent with what is here. So if we go in our practice problems, it's just the handout and example 6.1, okay? Any questions for practice problems in what we've gone over so far? Okay, so you have two really good examples of relative velocity in these last two examples that we did. What I'm going to do now is I'm going to stop the recording, and then we're going to look at the assigned homework that you have to kind of give you where you can look for good examples.